Swayam Prabha. Digital India. Educated India.
Today we will be talking about trajectory generation. What we have looked at in the last couple of classes is forward kinematics and inverse kinematics. So, in forward kinematics we are looking at the relationship between the joint variables and the end effector position and orientation, and in inverse kinematics we are looking at, given the position and orientation, how to find the joint variables. Now, in either of the two cases we did not talk about time. So, when we are saying inverse kinematics, we are simply saying that to reach a particular position and orientation in space, for example, my hand is here, I want to go to this position and orientation, what should be the joint angles. Now, this does not involve time in any way, but we know that to control the robot from one location to, from one position and orientation to another position and orientation, we have to also consider time. So, in trajectory generation what we consider is we fit a trajectory to each of the joint angles as it is moving, and in terms of position, velocity and accelerations, and there is of course time in the picture. So, today we will be talking about trajectory generation, which is more important from the point of view of control of the robotic system. So, let us proceed, and very briefly looking at what we were doing in the last couple of classes is we were talking about forward kinematics. So, we have a very simple two link system, just to revise a little bit. So, we have two links and there are two link variables, which is theta 1 and theta 2, and my end effector position and orientation is x y at the end effector. So, in forward kinematics what we do is we are given the input is theta 1 theta 2, which is the joint variables, and this is my forward kinematics, and what we get is the variables x y at the so, input is theta 1 theta 2 and the output is x and y. Now, in inverse kinematics what we are getting here is the desired is the end effector position and orientation, and this is my inverse kinematics equations, and what we get as an output is theta 1 and theta 2. Okay. So, if my joint was here, I want the link to move here, this is my position 1 and this is my position 2. So, this is my theta 1 dash and this is my theta 2 dashed. So, if I want to go from here to here, I can find out what is theta 1 theta 2 at this position. Let us call this position 1, and this position we call it position 2. So, in position 1 my corresponding theta 1 and theta 2 are giving some values. Let us say just for example, we say this is 30 degrees and theta 2 is 60 degrees. Now, in location 2 we say that this is my location 2. In location 2 my theta 1 is for example minus 20 degrees and this is about 30 degrees. So, essentially theta 1 has moved from 30 degrees to minus 20 and theta 2 has moved from 60 to 30 degrees. Now, you would remember that how does the robotic system actually work. So, at each of the joints we have an actuator, which is a DC motor or an AC motor, which has encoders, position sensors, and there is a gearbox in front. So, how does this robot move? We have at every joint we have a motor, we have an encoder, gearbox in the front. So, essentially from here to here we are actually actuating the joints. Okay. Actuating the joints means we are changing the variables, joint variables theta 1 and theta 2 in some time. So, this is where time comes into picture. Now, when we talked about forward kinematics and inverse kinematics, there was no time, but when we are talking of trajectories we have to consider time now. So, what we will say is this joint theta 1 has to move from 30 degrees to minus 20 degrees in say some time t 1. Okay. And joint 2 has to move from 60 degrees to 30 degrees in some time t 2. So, now time is in the picture. Now, with this definition what we will write is a trajectory. So, trajectory is essentially a time history. So, it is a time history of position, velocity and acceleration. So, it is a time history of theta, theta dot and theta double dot. Okay. Why do we need theta? We need theta because I want to go from one position to another position. Why do I need velocities? Because I need to control the velocities, the motor velocity has to be controlled, and we also need to control the accelerations. So, from control point of view I need these two, and I actually need all these three, theta, theta dot and theta double dot. So, a trajectory is defined as a time history of position, velocity and acceleration, and a path, we have seen a path. So, when I change the trajectories at the joint level, the end effector will have some path in space. For example, it moves like that, just for example. Now, this path is a function of joint variables. Okay. So, these are two things to remember. The first is what is a trajectory and what is a path. Now, a trajectory is essentially a time history of position, velocity and acceleration of the joint variables. Why? Because we are controlling the joints, and when we are controlling the joints, essentially as a result of that, the end effector is moving in space, and the final motion is my path now. Okay. So, let us take a very simple example. I have a very simple 1 degree of freedom system, just to make it simple. Okay. So, we have a 1 degree of freedom link, a rotatory joint which has only one variable theta. It is moving from some position here to some other position there. So, this is my theta at, let us say, call it at time t is equal to 0, and it has moved to this point theta dashed and time t is equal to Tf. Tf is my final time. Okay. So, this has moved. Now, this is 1 degree of freedom, one link rotating. So, this will have a arc in space. Okay. So, essentially what we are asking in trajectory generation is this theta is changing from theta to theta dashed in time Tf. What should be the equation of motion? So, I have to fit an equation which will essentially give me a relationship between the position in terms of and also time. Okay. So, now what are the various constraints on this? So, what are the various constraints? Now, before we go into the various constraints, we can say that if I talk about this 1 degree of freedom system and I plot, I am drawing my time axis here, this is my time, this is my theta. Okay. So, this fellow has moved from some theta naught, let us call it theta naught, okay, and let us call this theta dashed or theta f, the same thing. So, it has moved to some theta naught to theta f in some time t. So, essentially in time Tf, this is my time Tf, okay, this is my time 0. So, the joint has changed from theta naught to theta f in time Tf. Now, if I were to plot it, then what would this plot look like? Okay. So, what are the possibilities? There are infinite possibilities, of course. For example, we can connect it by a curve which is going like this. I can take a curve which is going like this. I can take a curve which is going like this. I can do all kinds of things. Okay. What about a straight line? Please think about this. Can I connect it with a straight line also? Okay. Is it possible to connect these 2 points with a straight line? So, the possibilities of connecting this theta naught to theta f in time Tf has infinite possibilities. Okay. So, we can have all kinds of curves. Now, so how do we decide what will be the equation of the curve? That is what we are trying to do in terms of trajectory generation. Now, if you look at this graph that I have just drawn, there are certain constraints that are coming into picture. For example, when the link was moving, it was at rest at this location here. So, the link was at rest at here, then it became at rest, it again moved and then came to rest. So, if I am saying my link is here, this is 1 degree of freedom system. Suppose I am explaining in terms of my hand, only 1 degree of freedom. It was here at time is equal to 0, it had some angle, say 30 degrees, and time is equal to Tf, it has gone here, okay, and time was Tf, maybe 2 seconds, 3 seconds, whatever, and the angle now is 60 degrees, for example. Okay. So, 1 degree of freedom, it moves from here to here in some time. I am asking the equation of the change of the angle here with respect to time. So, what are the constraints? There are 4 constraints. What are the constraints? One is it was at this location at time is equal to 0, then it went here at time is equal to Tf. Okay. So, there are 2 constraints. At time is equal to 0, it is at theta naught theta f. Okay. So, there are 2 constraints. So, theta at time is equal to 0 is equal to theta naught, okay, and theta at time is equal to Tf is equal to theta f. Okay. So, this is theta naught, this theta f, it has gone in time Tf. So, this is 2 set of constraints. What are the other 2 constraints? When the arm was here, it was at rest. When the arm has gone here, it is again at rest. So, at this location time is equal to 0, the arm is at rest. Again at time is equal to Tf, the arm is again at rest. So, from that we get another 2 constraints in terms of velocity. So, at time is equal to 0, the velocity was equal to 0. At time is equal to Tf, okay, it is again 0. So, we see that there are 4 constraints here. Now, with these 4 constraints, we can write, so we can fit an equation, we can fit a cubic polynomial. So, we can fit a cubic polynomial of order 3, because then we can fit in all the 4 constraints and write it in the form theta t is equal to a naught plus a 1 t plus a 2 t squared plus a 3 t cubed. Okay. So, we have 4 constraints, we have 4 constants a naught, a 1, a 2 and a 3, and we have 4 constraints. So, for each of this we can get one equation, and by solving them we can find what is the value of a naught, a 1, a 2, a 3. Okay. Now, we say that so this is my equation. Okay. This is a cubic polynomial of order 3. Now, we said that we also want the velocities and the accelerations also. How do we get velocity and accelerations? So, if I say this is my theta naught, the equation, if I write it again. So, theta in terms of time is equal to, so exactly the same thing here, I write it down, a naught plus a 1 t plus a 2 t squared plus a 3 t cubed. Okay. So, if I differentiate it once, I get theta dot, that is my velocity. So, which is equal to a 1 plus twice a 2 t plus thrice a 3 t squared. So, this gives me my velocity. So, this gives me my position, this gives me my velocities, and if I differentiate it again, I get here, and this I get in terms of my accelerations. So, what will be my accelerations? It will be twice a 2 plus 6 a 3 t. Okay. So, this is my accelerations. Okay. So, we said trajectory is a time history of position, velocity and accelerations. So, we can get our position from here. So, I can get my position, velocity and accelerations again. So, let us write down the equations again. So, my first equation was theta naught, theta in terms of time was equal to a 1, sorry, a naught plus a 1 t plus a 2 t squared plus a 3 t cubed, and I got my velocities by differentiating it, which is equal to a 1 plus twice a 2 t plus thrice a 3 t squared, and I got my accelerations from here, which is equal to twice a 2 plus 6 a 3 t. Okay. So, position, velocity and accelerations. So, this is my velocity and this is my accelerations. Okay. Now, how do we find the 4 constants a naught, a 1, a 2 and a 3? So, we look at the constraints. So, we had constraints here. What were the constraints? So, the constraints were given by, the first constraint was that at time is equal to 0, it was at theta naught. The second constraint was time is equal to T f, it is at theta f, and then in terms of velocity, the constraint was that time is equal to 0. Okay. The velocity was 0, and again time is equal to final time, the velocity was again equal to 0. So, we have 4 constraints and we have 4 constants here. So, this is 1, 2, 3 and 4 constants and 4 constraints. So, I will take each one of these constraints, put them in the respective equation, and I will get 4 equations. Okay. So, we have 2 in terms of position. So, this one and this one. So, I will put it in this equation, I will get 2 equations. So, I will take the first one at time is equal to 0. So, t is equal to 0, theta is equal to theta naught. So, theta naught is equal to a naught. Okay. So, from equation number 1 in terms of position, I am getting this equation. Okay. So, from this equation of position, I am getting the first equation. Okay. The second constraint I am putting again in my position equation, at time is equal to T f, theta is equal to theta f. So, theta f is equal to, at time is equal to, so it is equal to a 1 a naught plus a 1 T f plus a 2 T f squared plus a 3 T f cubed. Okay. So, we are getting one more equation by using these 2 constraints and putting it in the position equation. Now, we have these 2 constraints here, this one and this one, which we can put in the velocity equation. Okay. So, we will get 2 equations again. So, velocity is equal to 0 at start. So, when time is equal to 0, velocity is equal to 0. From that we get 0, velocity is equal to, time is equal to 0. So, a 1, it is equal to a 1. Okay. The other terms, this term and this term will be 0 because t is equal to 0. So, we get one equation here. Now, we put the second constraint, this constraint again into this equation. Okay. So, what do we get is velocity is again 0 at time is equal to T f. So, it is a 1 plus twice a 2 T f plus thrice a 3 T f squared. Okay. So, now we have we had 4 constraints and we have 4 equations. So, from here we can try and solve. We have already got the values of So, we can see here that we have already got the values of what this one, we have already got the values. Okay. So, this is the value I have got already for A naught is equal to theta naught. So, we have already got the value of A 1 is equal to 0. So, I am left with two more constants. So, this one and this one. Okay. So, I have two constants which I need to find, A 2 and A 3, and I have two equations. So, this is one equation 1 and this is my equation 2. So, equation 1, equation 2 I have, and I have two constants I have to find. So, I can try two equations, two constants. So, we can find the values of A 2 and A 3. Okay. So, if I solve for A 2 and A 3, what we do get is I will just write down the you can solve them very easily, and what we are going to find is that A naught is equal to 0, what we have A naught is equal to theta naught, what we have found A 1 is equal to 0, then A 2 is equal to 3 by Tf squared theta f minus theta naught, and A 3 is equal to minus 2 by Tf cubed divided by theta f minus theta naught. Okay. So, this you can very easily find from now. So, we have found A naught, A 1, A 2, A 3, and my equation was theta naught, my cubic spline was equal to theta naught is equal to A naught plus A 1 t plus A 2 t squared plus A 3 t cubed. Okay. So, this is my main cubic spline equation. So, this is my cubic polynomial equation, which is basically my trajectory. Now, in this equation we have found the values of A naught, A 1, A 2 and A 3. So, now I need to find what are the velocities and the how do I find the velocities? Velocity is essentially from this equation. Okay. So, here this requires A 1, A 2 and A 3. I can find the accelerations from this equation A 2 and A 3, okay, all of which are known. So, essentially what we can do now is, when we have found the constants A naught, A 1, A 2 and A 3, I can put them in this equation, differentiate it once, I get velocities, I differentiate it again, I get accelerations. Now, looking at this equation here now, what we can do is we can find at every instant of time, going back to our original equation, we said that we want to know that this is moving from theta naught to theta f in some time T f. Okay, this is my time T f here. Okay. So, this is my time T f, okay, this is my time axis, this is my theta axis. So, I want to go from here to here in some time. What will this curve look like? Okay, I am basically trying to say that this curve, what will it look like? Okay. Now, the equation of this curve would be given by this equation now. Okay. So, how do we find it? So, first of all, I need to find my 4 constraints. So, for a system, I need to find from where to where I want to go. So, if it is a 2 degree of freedom link like this, okay, I want to go from here to here in some time T f. So, this is my time theta naught, this is theta f, okay, it is going from here in time T f. I need to get the numerical values of theta naught and theta f, and then what is the time at which I need to go there. So, once I get that theta naught, theta f, velocities are always 0 at start and end. I can do what I can do is I can put them in this 4 equations and get the values of A naught, A 1, A 2, A 3, and then put it in this equation of motion. Now, once I get this numerical value of this A naught, A 1, A 2 and A 3, then I can plot this graph. How do I plot the graph? I know the total time is 0 to T f. Let us say, for example, T f is 5 seconds, just for example. So, what we can do is we can take the values of time at small, I can break this time axis into small intervals, say 0.1 second, 0.2 second, 0.3 second, just for example. Okay. So, I take 0.1 and I put it in t, and then find what is the value of theta naught. So, I plot it here. Okay. Then I take the next instant of time, which is 0.2, put it in this equation again, and then see what is the value of theta. So, probably it is here. So, I keep doing that and I get multiple points, and this points is basically what is my trajectory. So, after I get my points, what I can do, I can connect them with a curve, fine curve, and this is my trajectory now. Now, we come back to the original equation or the original question which I asked at the beginning of the class today, is that what will this trajectory look like? Okay. Is it going to be a straight line? Okay. Is it going to be parabolic? Okay. Now, if you think a little bit, this cannot be a straight line. So, if I were to just rub this off and make the assumption that this trajectory is a straight line, let me assume that this is a straight line. Okay. Now, the equation of a straight line would only contain this term and this term. Okay. Okay. That is the equation of this straight line. Now, if I differentiate it, what would happen is you will be getting theta. If I differentiate this, if you understand what I am saying, theta dot would be equal to a1 and theta double dot would become equal to 0, okay, if this equation was a straight line. Suppose I am saying that my equation of the straight line is this, and I am saying that I want to represent this motion with a straight line. Now, is it possible to have a straight line motion? So, if I differentiated 1, I am getting the constant velocity a1, and if I differentiate it twice, I am getting acceleration equal to 0. Now, you know that for a physical body to move, it is at rest. Now, to start from rest, it needs some acceleration. So, the accelerations cannot be 0. Okay. So, if you have a physical body which is at some point in it is resting somewhere and I want to move it, a link is like this, I want to move it from here to here in some time. So, in order to start moving the link, I have to give some acceleration. Now, if the acceleration is 0, obviously you cannot start. Okay. So, having a straight line motion like this is not possible, although it would appear to us that the easiest way would be just to move it in a straight line, but this trajectory cannot be a straight line. Okay. This just shows because accelerations are 0 and also velocities are constant. So, what we got here is theta dot is equal to a1. Again, velocity, constant velocity is not possible. Why? Because the system is here, it is starting and it is ending here. So, it has to start with some velocity, okay. It has to accelerate, means velocity is increasing. Then in the center, the velocities will again change, it will start decelerating. So, accelerations will start decelerating and then the velocity will come to stop. So, to start and stop, you need to have increasing velocity and then decreasing velocity. Similarly, you need to have high accelerations and then low accelerations, means acceleration and deceleration. So, a straight line does not enable you to do that. So, this essentially shows that the trajectory that we can fit is a cubic polynomial trajectory. Why essentially cubic polynomial? Because we have 4 constants, which is a naught, a1, a2 and a3. Now, you might want to know that what happens if I add a couple of more terms here. So, suppose I add a4 t raised to 4 plus a5 t raised to 5. Okay, I have added 2 more terms there. So, we have basically 2 more constants a4 and a5. Okay. How do we find that? Essentially what we need to do is I need to find another 2 constraints. Okay. So, here we have 4 constraints, 2 constraints on position, 2 on velocity. Suppose I add 2 constraints on acceleration now, then I can add 2 constraints on acceleration and find a4 and a5. Okay. So, the minimum is cubic polynomial, but I can go for a higher order also, but it is not generally done. Normally we use only cubic polynomials, but if you want to have a system where you are controlling jerk means controlling accelerations. In such cases we might have to have a controlled acceleration, in which case I need to add 2 more terms t4 and t5. Okay. But in this case we will just keep it with a cubic polynomial. So, this essentially shows that a straight line is not possible. So, the trajectory that we will be getting will be something like this, okay, where the system is starting, then it is going up and then it is the velocities are changing and then it is coming to rest. So, let us do a very simple problem in trying to understand that how do we actually enforce this kind of motion. So, we have got a cubic polynomial. Now, let us look at this problem. So, this is an example of a very simple example that I just drew some time back. So, it says that a single link robot with a rotary joint is motionless at theta is equal to 15 degrees. Okay. And so, a couple of points here. The first is that it is a rotary joint, single link robot with rotary joint. So, it is a revolute joint robot, okay, 1 revolute joint, and it is single link. So, it is 1 DOF, okay, and it has a rotary joint. It is motionless, means velocity is equal to 0. So, theta dot is equal to 0 at theta is equal to 15 degrees. So, initially it is at theta is equal to 15 degrees. It is desired to move the joint in a smooth manner to theta is equal to 75 degrees, okay, in 3 seconds. So, my theta f is equal to 75 degrees and the time tf is equal to 3 seconds. So, we are given that what are we given? Theta at 0 is equal to 15 degrees, okay. Time is equal to 0, it is 15 degrees. Now, theta at time tf, which is 3 seconds, okay, is equal to 75 degrees. This we are given. So, tf we are given is 3 seconds, okay. These things we are given. Okay. Now, it says find the coefficient of a cubic that accomplishes this motion and brings the manipulator to rest at the goal. Okay. So, these are 2 constraints. What are the other 2 constraints? So, theta naught at 0 is equal to 0, it is at rest when it starts and it is at rest when it stops. So, this is 3 seconds, also it is at rest. So, we have 4 constraints, okay, 2 on position and 2 on velocity. Okay. It says find the coefficients of a cubic that accomplishes this motion and brings the manipulator to rest, and also after finding that we are supposed to plot the position, velocity and acceleration of the joint as a function of time. So, if I draw it here, very simple case I am drawing. So, it is at 15 degrees. So, this is a one link rotary joint, okay, it is at 15 degrees. So, this is equal to 15 degrees here, okay, and it goes from here to here. Okay. So, let us say this is my, it goes from here to here, this is 75 degrees and this time is 3 seconds. So, velocity is 0 here and velocity is also 0 at the stop. So, this is what the question says. Now, we are asked to find the coefficients of a cubic polynomial. So, my cubic polynomial is going to become theta t is equal to a naught plus a 1 t plus a 2 t squared plus a 3 t cubed. Okay. So, we are asked to find what are the coefficients of this cubic polynomial. So, these are the coefficients or constants. Okay. So, I am asked to find this 4. Now, once I get that, we can put the values of time, different instance of sampling time, and then insert it into this equation and get what is the position, what does the final graph look like. So, so these are my 4 constants, and we have seen how to find these values. These 4 values we can find simply from here. So, what we will do is a naught is equal to theta naught, which is 15 degrees. Okay. A 1 is 0, it is given already. Now, T f is equal to 3 seconds, that we know, okay, and theta f minus theta naught we know, this is equal to 75, this is 75 minus 15, okay, and T f is equal to 3 seconds, that we know. So, I simply take the values, put it into this 4 equations and get the values of a naught, a 1, a 2 and a 3. So, once we get that, what we find here is, so let us put it in here. So, let us put in these values into this equations, and we get a naught is equal to, so a naught is equal to theta naught, which is equal to 15 degrees, then a 1 is equal to 0, okay. A 2 is equal to 3 divided by 3 squared divided by 75 minus 15, okay, and a 3 is equal to minus 2 by 3 cubed divided by 75 minus 15. Okay. So, the values come out to be equal to, so this comes out to be equal to 20 and minus 4. So, this comes out to be equal to minus 4.44. Okay. So, we have got our 4 coefficients. Now, what is the equation? So, it is a 1 t. So, theta t is equal to, so is equal to 15, a 1 is equal to 0. So, let me write down the equation here again, just to remember, is equal to a naught plus a 1 t plus a 2 t squared plus a 3 t cubed. Okay. So, this term is equal to 0. Okay. So, what we are getting here is the equation 15 plus 20 t squared. So, a 2 is equal to 20. So, minus 4.44 t cubed. Okay. So, this is my polynomial equation which we were asked to find. Okay. So, this is my cubic polynomial, right. Now, how do we get the velocity? I differentiate this equation, I get theta naught is equal to time. So, if I differentiate it, I get 40 t. So, this 40 t minus the 13.33 t squared. Okay. So, this is my position, this is my velocity. Okay. So, we get our velocity, and if I differentiate it one more time, I get t, which is equal to 40 minus 26.66 t. So, this gives me my acceleration. Okay. So, we have got our position, velocity and acceleration. Now, the question also says that first of all find the coefficients of the cubic which we have found in terms of a naught, a 1, a 2, a 3. Now, it also says after finding the cubic, plot the position, velocity and accelerations of the joint. So, when this joint is moving from here to here, what is the change of position, velocity and acceleration with respect to time. So, we have to plot that. How do we plot it? So, I have for position I have this equation. What I simply do is I change and time goes from 0 to 3 seconds. Okay, time is going from 0 to 3 seconds. So, in intervals of 0.1 second I put 0.1 into here, get what is theta naught, then I put 0.2, 0.3, 0.4 like that, see the corresponding theta and then I plot. That gives me the variation of theta with respect to time. Similarly, I also plot for velocity. So, I take the second equation. So, this equation I take for velocity, put the values of time as 0.1, I start off with 0.1, I take 0.1, put in this equation, get the value of theta naught t. Then I take 0.2, 0.3, 0.4 like that and simply plot the values of theta dot. I get the velocity of how the velocities are changing. Now, for accelerations again I take time is equal to 0.1, 0.2, 0.3 and 0.4 and in that order up to 0 to 3 and plot the various accelerations and see how the acceleration is changing with respect to time. So, I get 3 plots, one for position, one for velocity and one for acceleration. Okay. What would they look like? So, they would look something like this. So, this is my time axis. So, this is the position plot and this is my time axis. This is the position plot and this is my theta. Okay. So, the theta was changing from 15 degrees to 75 degrees in time of 3 seconds. So, this is 0 to 3 seconds, you can see here, and this is how the position changes. Now, you can see very clearly that it is not a straight line, okay? And we also said why it will not be a straight line. Now, when we come to velocity, we see that the velocity is this is velocity, this is theta dot. Okay, so, this is my theta dot. So, the velocity increases, then somewhere in the middle. So, the middle would be at 1.5 exactly. So, it is here. Okay. The velocity changes direction. So, it is increasing means it is accelerating, then the velocity changes direction and it is decelerating again. Okay. So, the velocity increases, then it decreases and this changeover takes place exactly at half the time, okay, because it is symmetric motion. So, when the arm is moving from here to here in some time, it will start accelerating till the middle, then it will start decelerating. Why? Because it has to start from rest and it has to come to end at rest, it has to come to stop at rest. Okay. So, this is again my velocity is my time on the x axis, and something to note here is that exactly in the center it is going to change directions. Now, let us look at accelerations. So, acceleration, this is my theta double dot and this is my 0 axis. Okay. This is 0, you can see that the 0 axis is here. Okay. So, this is my 0. Okay. Now, something to note here is that okay, so the acceleration graph looks something like this. So, this is my time axis, the x axis is the time axis, the acceleration axis is here theta double dot. So, when time is equal to 0, we see that the acceleration is equal to 40, okay, which is how did I get that? Essentially, we put our so onto this equation. If I put time is equal to 0, t is equal to 0 start time, I will get for acceleration is 40, okay. And if I put time is equal to 3 at the end, Tf is equal to 3, I will be getting acceleration is minus 40. Okay. So, essentially from here what I am getting is the acceleration graphs look something like this. So, it starts off with a very high acceleration of 40 and it ends also with a very high acceleration of minus 40. So, this is minus 40 here. Okay. So, the variation of theta double dot is from 40 to minus 40. Okay. Now, this gives me the position, velocity and acceleration plots. Okay. So, when we put our cubic polynomial, and what was our cubic polynomial? It was equal to theta t is equal to 15 plus 20 t squared minus 4.44 t cubed. Okay. So, when I put in this cubic polynomial and found theta, theta dot and theta double dot, the trajectory looks something like this. The change of position looks like this, change of velocity looks like this and change of acceleration looks like this. Now, the question that comes up here is that because we are talking of a robotic system has to move in the real world, which means that is this motion possible or not? Because if the motion is not possible, then obviously a robot cannot behave like this. Okay, it cannot move like this. Now, if you look at the position graph, the joint is not a straight line. So, it is possible for the robot to have this kind of trajectory. Okay. And the velocity also we know when an object starts from rest and it ends at rest, this is the velocity profile, it increases, decreases. But what about the accelerations? If you look at the acceleration graph, at time is equal to 0, acceleration is 40 Okay. When time is equal to Tf, acceleration is minus 40. Now, is that possible for a real body, okay, real object? Now, if you think a little bit, it becomes very clear that this is not possible. Why? Because when the object is at rest, it cannot have an acceleration of 40. Okay. Similarly, at the end of motion, when the body is again at rest, it again cannot have a very high negative acceleration of minus 40. Okay. So, this kind of acceleration is not possible in a real world, in a real situation. Okay. So, this although theoretically a cubic spline is fine, we normally represent motions by cubic splines, but in reality there is a problem at the start. So, at this position there is a problem, and at the end also there is a problem. Why? Because when the body is at rest, it can't have a very high acceleration. So, the problem is acceleration is 40 at start, okay, at time is equal to 0, okay, which is not possible. Why? Because when the motor, you would remember that at the end of the day the joint is actuated by a motor. So, when the motor starts, it will take some time to accelerate. Okay. The acceleration will not suddenly come from 0 to a very large value, because electrical motors have their own time constants, etc. Okay. So, the acceleration cannot come instantly to very high value, and because of which this kind of acceleration is not possible in a real system. Now, if this is not possible in a real system, then what is possible in a real system? What should we do? One way is, let us try and think that if this kind of a motion is not possible because of this problem with acceleration, that a motor cannot accelerate in 0 time, it cannot suddenly go to high acceleration. So, what kind of motion is possible? Then what we can think about is, we can talk of this graph. Let us say that we start slowly. Okay. So, my joint is here, it is going to go to this point. Okay. So, what we are doing is, we are going to start very slowly, then we will have linear motion, then we will stop very slowly. Okay. So, what we are trying to say here is that, let me look at it like this. So, we call it a linear function with parabolic blends. So, what we will say is, in this we are going to start very slowly. So, let me draw it here again. So, we are going to start very slowly. Why very slowly? So, that this acceleration will pick up like this slowly when the motor is taking time to accelerate. So, I am going to have a parabolic start like this. Okay. So, it is going to start very slowly like this from here, then it will become a straight line, then it will stop very slowly there. So, here and here we are going to have a parabolic blend here and parabolic blend here. Here it is more or less going to be a straight line. Okay. So, let me draw this again. So, essentially what we are saying is that we are going to start very slowly like this, and we are going to end very slowly like that, which is going to be parabolic, and in between both of this we are going to connect by a straight line. Okay. So, this is starting slowly, ending slowly, and I am going to connect this two by a straight line like this. So, this has 3 parts. There is one parabolic part here, one parabolic part here, and a linear part here, and this kind of motion is called linear function with parabolic blends. And why do we need to do that? Essentially because the motor cannot start with a very high acceleration initially, it will start slowly, and we say that the motion is going to be parabolic there. So, it will start slowly, then it is going to also end slowly. Instead of abruptly ending like this, it will end slowly like that. Okay. And our motion and the effect of it on the position would be having 2 parabolic parts and 1 linear part. So, this is my x and y axis. So, this is my x axis and y axis. So, I want to go from theta naught to theta f in some time T f. So, this is what I want to do in some time T f. So, what I will do is, I am going to start very slowly like this, and I am going to end very slowly like this, and in between I am going to have a parabolic part. So, there are 2 parts. One is there are parabolic blends. Okay. There are 2 parabolic blends and there is a linear part. So, this is my parabolic part, which we call it a parabolic blend, this part, and this part we also have a parabolic blend at the end part. This part is my linear part. Okay. So, what we are seeing here is that in a real system we try and make the motion such that the motor starts slowly, the motor ends slowly, and in between it is a linear motion. Okay. Linear motion means the velocity is going to become constant. Okay. Now, how do we model this kind of motion? Okay. So, let us look at it here. So, what we are saying here is that our motion would consist of linear function and 2 parabolic parts. Now, let us draw it here and see what are how can we derive the equations. So, let me draw it here. So, this is my x axis and y axis. some things to note here. So, this is starting point theta naught, it starts at theta naught, it ends in theta f in some T f. So, this is my start point T naught, this is my end point T f. Okay. So, it is going to start slowly like this, well it is not so large. So, let me, so it is going to start slowly like this, and in T f it is going to end. So, this is my T f. So, it is going to end slowly like that, in between it is going to become linear. Okay. So, this part is linear. Okay. So, okay. So, you understand that. Now, what we are seeing here is, okay, that is better. Now, what we are seeing here is that there are 3 parts here. So, there is another part here which is called T b, this is the time of blend. So, so the blending path starts from here T naught to T f. So, this is my blend part, okay, this is my blend part here, and it stops at this point. So, there is a blend part, then there is a linear part, and then there is a blend part again. So, this is my linear part, okay, this is the linear part which is going straight, and that is my blend part. Now, what we are doing, what we have seen also in our graphs is that in the center of the motion exactly here, which is halfway, this is going to become T h. So, this is halfway mark called T h, and in the halfway mark the velocity is going to change. This is what we have seen from here. So, we can see that exactly at the halfway mark the velocity changes direction. So, when we come to this T f, so this is my position, it has reached theta b, it has reached the position theta b, and this is my position theta h, halfway mark. Okay. So, let us look at the various terms that we have tried to include here. The first is that there is a blend portion which is going from T naught to T f. So, we have a blend portion which is going from T naught to T f, sorry not T f, this is T b, sorry this is T b here, it is going from T naught to T b, okay, and the position is varying from theta naught to theta b. Okay. Now, in the halfway mark, theta h is exactly the halfway, which is equal to theta is in between the mark of theta naught to theta f, and it is going in time T h. Okay, this is halfway, right. Now, when we look at this, what can we find from this, the way we have drawn the graph? The first part is that the acceleration by which at this point, at the end of the blend section, it will start from rest, it is starting from rest, slowly the acceleration is building up. Now, at the end of the blend section, whatever is the acceleration here, that is going to be the acceleration of the start of the linear section, right. So, when you look at it here, this section here, so it is starting from rest, the system was at rest, it is starting to move, the acceleration is building up. So, at the end of the blend section, whatever is the acceleration, that acceleration is going to be the start acceleration of the linear section. Okay. So, what we can do is we can derive the equations and try and see if we can come up with the relations. So, now suppose we say that the acceleration of, so let us say let the acceleration at blend section be theta double dot. Okay. So, this is my blend acceleration of theta double dot, right. So, what is the velocity at the end? So, we see the velocity. Now, the accelerations are here. Now, what about the velocities? The velocities, the same logic applies. So, the velocity will start from 0, then the velocity will build up slowly till here. Now, whatever is the end of the velocity here, that is going to end. So, that velocity is going to continue in the linear section here again, right. So, the system is going to start with lower velocity, sorry, it is going to start with 0 velocity, then the velocity is going to pick up. Okay. Now, when the velocity picks up to this position at the end of the blend, the end velocity at the blend section is going to become the start velocity of the linear section, okay, because it is continuous there. So, what we can do is from our equation v is equal to u plus at, okay, this you know from physics, that the final velocity is equal to initial velocity plus acceleration into time. If using this equation, we know that the initial velocity was equal to 0, the system was at rest. So, we get v is equal to at, right. Now, what is at? This is equal to a was equal to acceleration, which is theta double dot, and what is time? Time is equal to T b. Okay. So, theta dot into T b is what we get, right. Now, so that is my velocity at the end of the parabolic section. Now, in the start of the linear section, it is a linear section. So, the velocity is going to be constant. Okay. So, please note here that the accelerations are going to your velocity will be constant. Why? Because it is linear in a linear system, not in a linear system. When it is moving in a linear way, the velocities are constant, right. So, if the velocity is constant in the linear section, so for the linear section, constant velocity, constant average velocity is there, and this constant velocity is equal to, so it is theta h minus theta b. Okay, so it is this distance. So, this distance by this time is equal to theta h minus theta b, right. So, this is my linear velocity which is coming here. So, the velocity at the end of the blend section must be equal to the velocity by which at the linear section. So, if I equate this to this, I get one equation. So, theta double dot T b is equal to theta h minus theta b divided by T h minus T b. So, this is my equation 1, right. And how did we get it? Essentially from the velocities. Velocity at the end of the blend will become equal to the velocity of the start of the linear section. Okay. Now, what else can we see? The other thing that we can see here is the distance that it is going to move in terms of theta. So, it is starting from theta naught and it is ending at theta b at the end of the blend section, right. So, if I am going to use my equations, so it is starting at theta naught, it is ending at theta b. So, I can say theta naught is equal to theta b plus half dt squared. So, again from physics we know that the distance formula. So, our distance formula tells us that using our distance formula I am going to get theta b is equal to theta naught plus half at squared theta double dot plus Tb squared. This I am getting from my distance formula. So, this basically says that I am starting at theta naught, I am ending at theta b. So, it is equal to theta b is equal to theta naught, this was already there, okay, plus half at squared. Now, how do I get this? We get it from our formula. If your s is equal to ut plus half at squared, we get from this distance formula. U is equal to 0. So, this part is 0, okay, and this part is half at squared, which is coming here, okay, and it was already at theta naught. So, theta b is equal to theta naught plus this term. Okay. Now, so this is my equation number 2, two equations. Now, the other two equations that we have is time is equal to, the total time is equal to 2 plus, so Tf is the total time is equal to 2 times half time. So, this is essentially the way we have drawn our graph, exactly the halfway mark is Th, and which is equal to half of the total time Tf, right. And so, so this is my third equation. Okay. Now, if I combine equation from equations from equations 1, 2 and 3, if I combine all of them, what we do get is this final equation Tb squared. So, we have Tb here, theta f minus theta naught is equal to 0. Okay. So, combining all these three equations, what we get is one final equation of this form. Now, so this is in terms of Tb. Basically, what we are trying to do is we are trying to find where this where Tb should be. For example, if the acceleration is very slow, it is starting, Tb is going to be going to shift more towards the right. If acceleration is very fast, then Tb will shift towards the left. So, Tb is not a fixed point. So, depending on the motor acceleration or the amount of acceleration it can give, the Tb is going to move towards the right or move towards the left. Okay. So, we are trying to find, are there any conditions on Tb? Okay. That means, is there a minimum Tb that you have to satisfy? So, from this equation, this is a second order equation T squared. So, this is a second order equation of the form mx mx squared plus bx plus k is equal to 0, and we know the solution of this. So, this is similar to this, right. So, this is my m, this is my b, and that is my k. So, I know the solution of this is Tb is equal to T by 2 minus root over theta dot squared into t squared minus 4 theta dot into T f minus theta naught divided by 2 theta naught. Okay. Now, here we do find that what is happening is that there is a term under the root. So, this basically says that this term under the root, this term here has to be positive, otherwise what will happen, time will become negative. Now, time cannot become negative, you know that when a system is moving in the real world, there is no meaning of negative time. So, this always has to be positive, and for that condition theta double dot must be greater than 4 theta f minus theta naught divided by t squared. Okay. This condition has to be satisfied for positive time, for positive Tb. Okay. So, this is the condition that what motor acceleration should you choose? Now, you have to choose an acceleration which is going to satisfy this condition, otherwise what will happen is the Tb will start becoming negative, which is not possible. So, this gives us the condition for Tb. Now, let us look at the same problem again. Okay, we come back to the same problem that we were talking about. We had a rotatory link, we just solved some time back, it is moving from 15 degrees to 75 degrees. So, this is my link which was moving from 15 degrees to 75 degrees in time. So, 15 degrees to 75 degrees in time 3 seconds, the same problem. But now, we are going to move this in a with a linear function with parabolic blends. That means, I am going to divide my motion into 2 parts. One is going to be a parabolic part like this, then will be another parabolic part like that, and in between I am going to have a straight line like that. Okay. So, this is what I am trying to do now. Okay. So, this is my time axis. So, this is my time Tb, this is my Tf, okay. This is my Th. So, we have all the values. This is my time, this is theta h, this is the final theta final, this is theta naught, all the values, this is a theta blend. So, all the values are known, this is my Th, right. So, all these values are known here. So, in the problem it is all given. So, theta naught is equal to 15, theta f is equal to 75, Tf is equal to 3. Okay. So, what we have to find is what is going to be Tb. Okay. And how do you find Tb? I have to come back here and then we have to choose a motor acceleration. So, from here we have to choose some motor acceleration. Okay. And for different motor accelerations, obviously Tb is going to change now. So, we are seeing 2 cases. So, case 1 and case 2. Okay. So, case 1 we see a low motor acceleration, motor theta double dot, and here we see a high motor theta double dot. So, what will happen is if I give a low theta double dot, this Tb will go towards the right, and if I give a very high theta double dot, it will go towards the left, right. So, again we follow exactly the same procedure. I find out what is the corresponding Tb, I can compute from this equation and this equation, right. I can compute from this equation, and then I plot for position, velocity and accelerations, and what we get is this. So, this is the case 1 where we are having different accelerations, okay, with parabolic blends. So, this is a case where we are having here what we are doing is a high acceleration and a low acceleration. So, this is the case 2 is reversed. So, this is essentially a high motor acceleration and this is a low motor acceleration. Sorry, this part was reversed, right. So, we are finding out the graphs. So, this is my position graph. So, this is position, this is case 1, this is case 2. Okay. So, in this case 1 we find that the variation of the position is like this is my theta. So, it starts like this, the parabolic section is very small, you can see that, then there is a linear section which is long, then there is a parabolic section again. Now, in case 2 where the motor acceleration is low, what we can see is that the parabolic section is more pronounced, it is going on. So, Tb is going pretty far, is going till here. In this case Tb was very small. So, Tb is small, here Tb is large, okay. And then it is having a linear section which is small, and then we are having a parabolic section again. So, depending on what accelerations we chose, so theta double dot was high here and theta double dot was low here, okay. So, depending on what we chose, the position variation is going to behave that way. Second graph shows the comparison for the 2 cases for velocity. So, you can see that the velocity increases very quickly and it is constant in the. So, correspondingly if I draw here, they correlate. So, I can correlate these 2 graphs this way, okay. So, this point corresponds to this point, this corresponds to that point. So, it accelerates, the velocity increases, then the velocity remains constant in the linear section. So, this is my linear section, then the velocity comes down and becomes 0 again. In the second case, where you had very slow acceleration, the velocity increases. So, this is corresponding upwards like that. Okay. So, it is corresponding like that. So, what is happening is this is corresponding to my point Tb, this is corresponding to Tb, this also corresponding to Tb. Okay. So, this is corresponding to the point Tb. So, you can see that the acceleration in velocity increases slowly, then there is a linear section which is very small, then it decreases slowly. Now, essentially it is because of the accelerations. Now, the third graph shows the accelerations for the two cases. This is case 1 and this is case 2 again. So, we saw position, this is position, this is velocity. So, this is theta, theta double dot, theta dot. So, this is theta and this theta dot. Now, we are seeing for accelerations, this is theta double dot, this theta double dot. For case 1, what we see is the acceleration is high, it is about 40. So, there is high acceleration, and then for a very short period, then it comes to a 0 acceleration, remains constant, then comes down, and then comes to 0 again. In the case of a low acceleration, we see it is about 25, 26 here. So, the acceleration is from a larger period of time. This is my Tb, correspondingly it will be Tb here, correspondingly it will be Tb here. So, accelerations are large, then it comes down to 0 acceleration, then again there is deceleration. So, this is an improved period where we are having a very small acceleration when the motor is just accelerating, then it is keeping a constant velocity, and then it is having a negative acceleration. Okay. In both the cases, this case shows the effect of theta double dot on theta, theta dot and theta double dot. Okay. So, this today's discussion was essentially about how to find trajectory. We have seen that essentially for simulations we still use cubic splines. Why we use cubic splines we have explained, and the problem of cubic spline in a real system is that a real system cannot accelerate in 0 time. Okay. So, what we do is we start the acceleration slowly and give it a parabolic blend there. So, we call it a linear function with parabolic blends which a real system can follow, and depending on the motors you are using, we can choose a low acceleration motor or a high acceleration motor, and based on that we can plot our position, velocity and acceleration and see whether it is satisfactory. So, this is essentially to show that in a real system we can follow a linear interpolation with parabolic blends. Okay. And so, today we end here. So, thank you.